Hello everyone! The question about the flat earth today actually comes from a student of mine, and this student is pretty interested in talking about, I guess you can think about them as fringe conspiracies, or just interested in what people think that is not necessarily mainstream. So they have a lot of discussions with people on places like Discord and Reddit. They were in a flat earth Discord and talking about just different things about the flat earth, I suppose, when they were presented with these 4 images that I'm going to show you first, and then we're going to get into them a little bit more deeply. And they were presented with these 4 images, so they sent them to me and said, hey teacher, you know, I'm in this flat earth chat, and quite frankly, this stuff looks really compelling. It looks like they have a lot of evidence to support what they're saying. What do you make of it? The reason that this student asked me is because, number 1, I taught them geography, but number 2, a lot of this stuff is from NASA or the Army, and they know that I did serve in the Marines. And number 3, the student knows I have a background in engineering, and I worked as a drafter for a while before I was actually in the military. So what are we talking about here? As we go through these, there's sections that are highlighted. I'm just going to read the entire section, not just the highlighted portion, okay? So please bear with me if any of this causes you to have any physics flashbacks or just sounds like a bunch of jumbled words that you don't really understand. Please bear with me. There is a method to this, or there's a reason for it. A linear aircraft model for a rigid aircraft of constant mass flying over a flat, non-rotating Earth is derived and defined. The derivation makes no assumptions of reference trajectory or vehicle symmetry. The linear system equations are derived and evaluated along a general trajectory and include both aircraft dynamics and observation variables. The next one is from NASA. The first one was also from NASA, by the way. The helicopter equations of motion are given in body axes with respect to a flat, non-rotating Earth. The helicopter is considered a rigid body with mass symmetry about the x sub h equals f sub h plane. The effects due to the engine angular momentum are neglected. Next, we have, from an Army website, Projectile Flight Dynamics. A 6-DOF rigid projectile model is employed to predict the dynamics of a projectile in flight. These equations assume a flat Earth. The 6-DOF comprises of 3 translational components describing the position of the projectile's center of mass, and the 3 Euler angles describing the orientation of the projectile with respect to the Earth. Figures 1 and 2 provide a visualization of the degrees of freedom. And finally, again from NASA, trajectory simulation. We're going to read the second paragraph only. A trajectory simulation incorporating the above requirements is presented in reference 8. In addition to the above requirements, the simulation assumes a vehicle with 6 degrees of freedom and aerodynamic symmetry in roll, and the missile projection or position in space is computed relative to a flat, non-rotating Earth. This trajectory simulation was programmed for the on the IBM 704 electronic data processing machine and is the basis for all trajectory computations made in this paper. If we do want to read the trajectory requirements, the above requirements are: the requirements for a trajectory program needed for a wind compensation procedure are, number 1, that the trajectory be 3-dimensional, number 2, that the provision be made for arbitrary wind velocity and azimuth, and number 3, that the nonlinear aerodynamics with respect to the flow incidence angle be included. The first 2 requirements are obvious since, in consideration of the side winds, the trajectory is 3-dimensional and the wind velocity and azimuth are arbitrary. And the third requirement is imposed because the introduction of winds or surface winds during the launch can create angles of attack larger than 90 degrees, which greatly exceed the linear range of the aerodynamic coefficients. If any of that was confusing to you, congratulations, you are most people. And I don't mean that you're uneducated or that you're stupid or anything like that. There's just stuff that a lot of people don't necessarily understand, and a lot of that has to do with mathematics, physics, and engineering, okay? Again, that doesn't mean that you're stupid. There's a lot of things I don't understand. The issue is that if I don't understand something, and there's a section that I read that seems very strange to me, such as the highlighted part here that says a flat, non-rotating Earth, I have to ask a person who understands this. And that's what the student did for me. They had to come and ask me because they didn't understand this. So that's kind of what I want to drive home here, is that if you're reading this in context and it all just sounds like a bunch of flibbity-jibbity kind of nonsense words put together, or a bunch of words that you individually understand what they mean, but put together it all just sounds like nonsense, ask somebody that knows what they are, because otherwise you're going to have a really hard time trying to follow along what it means, and you might end up coming to some conclusions that are incorrect. So that is why you want to ask. Even if you're kind of sure what it means, it's always a good idea to ask somebody who has a background in this type of thing. So let's go back to the first one. We can actually see here that we're going to start off with a flat, non-rotating Earth derived and defined blah, 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 and then we're actually going to start adding other variables. And in fact, in the bottom it says here, observation variables. This comes from a paper that is here from 1988 called The Derivation and Definition of a Linear Aircraft Model. So that's what we're talking about here. Now, don't worry, we're not actually going to go through the whole thing because we actually do not have to. The reason that we're starting off here with things like a flat, non-rotating Earth and then later evaluated along general trajectory to include both aircraft dynamics and observation variables is because we first want to get rid of as many variables as we can. There's sort of a joke or phrase if you talk about like physics where you can say I don't want to botch this, but it's been quite a while since I've been in school, but how much leather can you get from a cow? And so a physicist says, well, first we assume a spherical cow. Now, does a spherical cow exist? No, there's no cow that's just a ball that exists on a farm somewhere. But if we assume a spherical cow, we know how to calculate the surface of a sphere, and so we can calculate the amount of leather that we can get from this spherical cow. And that's sort of what we're doing. We're taking things that are not realistic so we can bring them down to a single variable, so we can start to calculate and understand what things we have to figure out, how it's different from something that we already know, and then we start adding in the variables. And in fact, we can actually see this right here in section 1.2.4, Earth relative velocity. This means that to an observer, we understand the Earth is moving and also the aircraft is moving, and now how do we calculate that relative velocity? That's what it's talking about. So we don't even need to go into the rest of this to show that this is that NASA doesn't think the Earth is not rotating, because right here it shows we're making a calculation based on a rotating Earth. So we do again want to start off with assuming the Earth is not rotating so we can understand just the issue with things like takeoff, landing, how the aircraft can handle different winds from different angles. And then we're going to add in the other types of variables, and that's all we're talking about. That's it. The next one, we're talking about a helicopter. So we need equations for helicopters because there's not just one type of helicopter. I know a lot of people think about helicopters as these news helicopters. We see these a lot in movies, for example, especially action movies. Or there's people that think about like these Korean War helicopters because, they used to see them in MASH. But there's actually a lot of different types of helicopters. The helicopter in question that the NASA document is referring to is the CH-53 helicopter, which is a pretty cool looking helicopter. And we can actually see in this image, it's carrying this, looks like a Humvee. This is a big honker of a helicopter, okay? Maybe you have seen something like this in some war movies where people might be hanging out the side and shooting or something. This is a massive kind of helicopter. This is why we need to calculate its physics, because it's not the same as a helicopter like this little guy here. Okay, and there's other types of helicopters, of course. When I was in the Marines, we had the Sea Knight, and then we also had the Osprey, which I saw a lot more commonly. And the Osprey is really cool because it actually can take off and land vertically, which is the big benefit of a helicopter. But one of the problems of a helicopter is when it's in the air, it's a lot less stable than an airplane. So the Osprey can actually have these moving propellers, so it can actually turn into, quote unquote, an airplane. So it's really, really cool. That's going to have different calculations for it as well, right? And that's all this is talking about. So when we go to this mathematical model of the CH-53 helicopter, you can actually look up mathematical models of other helicopters too. And again, all we're trying to do is calculate and understand what different issues that we're going to have to deal with. How is this helicopter's weight different? What is the angle of the blades, the length of the blades, the width of the blades? Is this helicopter able to handle certain situations of high winds or that sort of thing? That's what we're looking at. So again, we're going to assume a spherical cow and try to get rid of as many variables as we can, including the rotating Earth, including the spherical Earth. Okay, so that's all we're doing here. And that's all this is. It's just, hey, here's a helicopter. It's kind of new. Let's check out what it can do. Okay. And in fact, like the first few pages of this are just all variables, 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 variables. Okay. When you see how many variables that we have to go through, look at this. Just appreciate this. Now you can kind of understand why we want to get rid of a lot of other variables first. And so some of these we're going to just assume that it is, for example, when we talked about vehicle symmetry, we're not even going to calculate that at first. We're not talking about these different situations first. We're just trying to figure out how does this thing go in the air and how wide can the propellers need to be, what is the angle that they need to be placed at. We're not going to assume every single possible variable. Like, what if the pilot is really tired that day? What if we end up flipping upside down? How can the helicopter fly successfully if we're upside down? Well, what if the bolts are rusted and part of the helicopter falls open and now we have to calculate our aerodynamics because one of our doors is open? We're not calculating that stuff. Could that happen? Sure. Might we need to calculate that later? Yes. But right now, we're just trying to think of how do we get this big, massive boy off the ground. Okay, that's what we're calculating first. All right, so hopefully that kind of explains it a bit more. This is another mathematical model of a different type of airplane, or sorry, helicopter. And so again, every time we have these new helicopters, we just need to do this same thing. And we're always assuming the spherical cow. Okay, we're always getting rid of as many variables as we can, because if you can look at this, look at how many variables you have to deal with for these helicopters. Of course, you want to get rid of as many variables as you can because you're still left with a bajillion variables to calculate. As for this guy, the projectile flight dynamics, what is this thing that we're talking about? So this, you can actually kind of guess right away exactly what we're talking about because we're adding liquid payload effects to the C-2 or DOF trajectory of spinning projectiles. In other words, if you have a missile that now has a liquid payload, these are things that the missile needs to carry and transport, usually to make a go big boom, okay? If I need to put something in there that's liquid instead of solid, that's going to be a different calculation. The example I gave to the student is I said, what if you have a mug and it was filled to the top with Hershey's Kisses, and I needed you to run from my classroom all the way to the front of the school? How fast could you do it? And so they assumed, oh, I don't know, 1 minute or less. Okay, cool. What if instead of being filled with Hershey's Kisses, it was filled to the top with hot chocolate? How fast could you run from my classroom to the front of the school without spilling any? And he said, well, I'd have to go a lot differently. Exactly. Because when you start walking and you're carrying something that's liquid, anybody who's had a little bit too much coffee or tea in their mug knows you have to walk a lot more slowly than if you had something more solid in here, coffee beans in here, or nothing in here, right? That movement of a liquid has different physics. And because of that, it's going to react differently than something solid in here. And that's all we're calculating here. So again, we don't really care about the Earth being flat. We don't really care about the Earth moving, non-moving, whatever. We want to get rid of as many variables as we can, assume a spherical cow, because right now we need to figure out how can we put a liquid in here without having our missile suddenly start spinning out of control. And that's the idea, okay? Then once we do that, of course, to calculate ballistic trajectory, of course we have to understand how far we're launching it, and then what's the angle of the curvature and all of that stuff. But the first thing we need to do before that is figure out how can we just make this thing fly straight. That's all we're caring about at this step. We can't launch it far away and have to calculate the Earth's curvature if we can't even launch this thing without it spinning out of control immediately after launching and crashing and exploding in front of us. Do you know what I'm saying? We can't figure out how to get it from point A to point B until we can figure out how to launch it successfully without it spinning out of control and exploding in our face. So that's step one. Step two, yeah, we get to that calculation point for long distance, which would include the Earth's curvature. But step one is how do we even launch this thing and make sure it doesn't get off of course. So that is what we're doing here. This last one here for the trajectory simulation, we're going to go to this technical note, calculation of wind compensation for launching unguided rockets. Hopefully from the previous one, you can immediately see what we're caring about here. We're caring about how the wind is affecting the launch. That's what we care about. This actually comes from a longer grouping of stuff here. Let me see if I can find it. Yes, so this is the organization for the collection, okay? This is a huge collection of different types of things that are related to the stability of launching these unmanned rockets or these unguided rockets, okay? This is one of many papers to calculate different variables. So it's cherry picking in this sense to find the one that doesn't reference the Earth, because we don't need to reference the spinning or the curvature of the Earth. We're just talking here about wind compensation. That's like if I was to say something about how fast you can drive on a bridge if your car is very small, and then you say something like, well, Miss Lemon is saying that we don't have to pay our taxes because in part of this it says we assume that we assume no price of the car. So she's saying that we don't have to pay taxes and we can steal cars. That's not what I'm saying. I'm saying we don't assume the price of the car because it's totally irrelevant to what we're talking about, which is the wind effect on our light little car as we're driving over a bridge, right? We don't need all these other variables. These are variables you might have to factor in later on for whatever reason. This is not a variable we're calculating now, so we're leaving it out, and I'm telling you that. So does that mean that I'm encouraging you to steal cars? No, I'm just saying for this calculation, we don't need that information. That's all it is. Later on, we might need it, and of course, there's going to be calculations for that to include that, but this is what it's talking about. So if I'm sending a rocket anywhere, if I'm sending it straight off into space, or if I'm trying to send it from one point on the Earth to another point on the Earth, cool. But right now, all I care about is the wind compensation. How is this going to affect the aerodynamics of it? So that's what I'm calculating here. I'm calculating aerodynamics. I'm not calculating how to successfully land in another area, which would include the curvature of the Earth. Okay, so that's why we have that. And again, you guys can go through this. All of these links are going to be in the details section below. Okay, that's all this was. Now, when I was trying to explain this to my student, this actually took a while. I had to make sure the student understood this stuff, and I had to go find all the information as we were talking about it, and of course this was in text, so this took about an hour or so to explain. And so my student had finished and said, wow, you know, that was really informative, I totally get it, you should come to the group chat and explain it. And I said, listen, you know, you have to be careful with that, because how long did this take me to explain this to you? And if somebody just assumes already that I'm a liar or that I'm part of the, you know, big NASA Illuminati conspiracy or something, they would just say, all this information that you told me, who cares? You're part of, you know, the wrong side or whatever. So this is something that you have to come at with the idea that perhaps I don't know everything and somebody knows more about me than this. Now, that doesn't mean that I'm smarter than you. There's stuff that that student knows that I don't know. They know way more about building game systems. I don't know anything about that. They know more about world building and level building in games. Cool. I don't know anything about that either. So the student is smarter than me in that way. And I think that's what we have to remember. If somebody knows more about you on a certain topic, listen to what they have to say. It doesn't mean that they're saying you're stupid. It doesn't mean that they think you don't know anything. Their knowledge on a subject is in no way a statement about the state of your intelligence. Okay? So please understand that. When I'm sharing this information with you, I'm sharing this information with you. I'm not saying you're stupid for having believed in it. I'm not saying that you're gullible and all this other stuff. I'm just saying, hey, I have a background in this. Let me share this information with you. I did want to make a note that there is these watermarks, or there are these watermarks here. I tried to go here. It appears to be www.fireandgracechurch.org. When I went there, it just appeared to be a regular church. I suppose we can all just go there right now. Fireandgracechurch.org. You can see I already did that search. And once I was here, I couldn't really find anything. I tried going to homeschool. I thought that might have some information. It just says basically we offer homeschooling books. Okay? You know, about us. Is there anything here? Our beliefs, maybe? That might be here. We believe Jesus Christ. I mean, this is a very normal kind of thing for churches to put. So I don't know why this was referenced on these. This is referenced several times on these. I don't know why it is. And again, I feel like a better place to refer to it would just be this link, right? Or to the PDF. I guess not this particular link because that's a saved PDF on my computer. Or this link, okay? Let people see the actual source of the document. What's the document even talking about? Why is it talking about it? Okay. Hopefully this has been helpful. If you guys do have any questions about flat Earth or any other types of conspiracies, please let me know. And I am happy to discuss them if I have the appropriate background. If it's something that I'm really, really clueless about, then I will ask other people to try to explain it to you. Maybe have them on my channel at some point to try to explain it as well. Anyway, I will talk to you guys later. Have a good day.